Hello everyone, and welcome to Abarso's 10th grade math Google Classroom. Each week we will have an instructional YouTube video and quiz to help you stay on top of your classes. The topic for this week is the remainder and factor theorem, which is directly related to your competency on explaining the relationship between zeros and factors of polynomials. As you follow along, take notes on these examples and definitions that are provided. These will be useful guides and can be used on the short quiz associated with this lesson. If you don't have them already, pause the video and grab your pen and notebook before we get started. Right, in order for us to get our minds thinking in the right direction, let's start with the do now. Today's do now should be a review from all the way back in primary math. However, it is directly relevant to our work today. For the following division problem, I want you to state your answer as a whole number and a remainder. Pause the video as you solve this problem. Now that you've had time to solve this equation, let's go over the answer. When our dividend 9 is divided by our divisor 4, we get our quotient, which is equal to 2, with a remainder of 1. This can be rewritten such that our dividend 7 is equal to our divisor 4 times our quotient 2 plus our remainder of 1. While the arithmetic in the do now was probably mental math for you, the underlying logic of our solution can be applied to more complex problems involving polynomials. In general, if we take f of x divided by d of x, we get q of x with the remainder of r of x. Just like we did in the do now, we can rewrite this into a form that's easier for us to manipulate. F of x equals d of x times q of x plus r of x. Defining each term in the rearranged polynomial, we get f of x is our dividend, d of x is our divisor, q of x is our quotient, and r of x is our remainder. Let's do a practice problem similar to our do now, but using polynomials. Let's divide the polynomial 2x squared minus 5x minus 1 by the quantity x minus 3. We can define our terms. F of x, our dividend, is equal to 2x squared minus 5x minus 1, and d of x, our divisor, is equal to x minus 3. Now we just need to perform some simple arithmetic to get our quotient and remainder. When we divide f of x by d of x, we get 2x plus 1 with a remainder of 2. We can define 2x plus 1 as q of x, our quotient, and r of x, our remainder, is equal to 2. If we want to check our solution, we can substitute our answers into the general form we derived in the previous slide. That is, we can check using the form f of x equals d of x times q of x plus r of x. Substituting in, we get 2x squared minus 5x minus 1 equal to the quantity x minus 3 times the quantity 2x plus 1 plus 2. When we simplify the right side of the equation, we get 2x squared minus 5x minus 1, which is equal to 2x squared minus 5x minus 1, so our answer checks. Note that another way of checking to make sure you are on the right track is by comparing the degree of our r of x and d of x terms. The degree of r of x must always be less than the degree of d of x. If this isn't the case, you know you need to check your work for mistakes. Now I know long division is not everyone's favorite operation to perform, so what if I told you there was a way to solve problems like the one we just did without long division? The remainder theorem helps us do just that. The remainder theorem states that when we divide a polynomial f of x by the quantity x minus c, the remainder is equal to f of c. Let's prove this before we move on to an example. When we divide f of x by the simple polynomial x minus c, we get f of x equals the quantity x minus c times q of x plus r of x. The quantity x minus c is of degree 1, which means r of x must have degree 0, so is just some constant r. Therefore, f of x is equal to the quantity x minus c times q of x plus r. Now see what happens when we have x equal to c. F of c is equal to the quantity c minus c times q of c plus r. f of c is then equal to 0 times q of c plus r, simplifying f of c is equal to r. This means that when we want to find the remainder after dividing by the quantity x minus c, we don't need to do any division at all. We simply evaluate f of c. Let's revisit the example we did previously, 2x squared minus 5x minus 1 divided by x minus 3. Instead of doing division, the remainder theorem tells us that we evaluate f of c equal to r. In the context of our problem, this means that if we evaluate 2x squared minus 5x minus 1 at x equals to 3, f of 3 should be equal to 2. Let's give it a try. Substituting in our 3, we can see that the remainder theorem checks. Let's try another example using the same dividend, that is, 2x squared minus 5x minus 1, but with a new divisor. Let's say the quantity x minus 4. In order for us to solve this problem, we simply apply the remainder theorem. Rather than dividing our f of x by the quantity x minus c, we simply have to calculate f of c. So in this example, this means we evaluate our 2x squared minus 5x minus 1 at x equals 4. Substituting in the value of our x variable, we get 11. What if we calculate f of c and we get an answer of 0? In other words, what if we get a remainder of 0? Remember, if a divisor evenly divides a dividend and we get a quotient with no remainder, then the divisor must be a factor of the dividend. The factor theorem tells us that when f of c is equal to 0, then the quantity x minus c is a factor of f of x. The other way around is true too. That is, when the quantity x minus c is a factor of f of x, then f of c is equal to 0. The factor theorem is easier to see with an example. Let's start off simple. Consider the following problem. 80 divided by 20 equals 4 with no remainder. This means that both 20 and 4 are factors of 80. This easily checks. 4 times 20 equals 80. But this also applies to polynomials. Take, for example, the function f of x equals x squared minus 3x minus 4. Let's evaluate the function at f of 4. F of 4 is equal to 4 squared minus 3 times 4 minus 4. Simplifying, we have 16 minus 12 minus 4 equal to 0. Since f of 4 equals 0, then the quantity x minus 4 must be a factor of x squared minus 3x minus 4. If you think back to what the remainder theorem told us about the quantity x minus c, then this point should be obvious. However, if you want further evidence, we can check by simply factoring the expression x squared minus 3x minus 4 into two binomials, which you have had plenty of practice doing. X squared minus 3x minus 4 is equal to the quantity x minus 4 times the quantity x plus 1. We see that the two factors are x minus 4 and x plus 1. If we set each factor equal to 0 and solve, we get the following solutions: x equals 4 and x equals negative 1. By finding zeros via the shortcut method, we apply concepts from the remainder and factor theorems in a quick and easy way. Now try your hand at it. Simply factor the expression, set each binomial factor equal to 0, and solve. Pause the video and give it a shot. Right, so the zeros for the expression x squared minus 16x plus 63 are 7 and 9. Easy, right? Now it's your turn to practice applying the remainder and factor theorem. Pause the video and solve the following problems before checking your answers. Thank you for tuning in. Hopefully you were able to follow along and understand the remainder and factor theorem and their relationship to the zeros of a polynomial. Check out the links in the description below for further resources to help you master this topic. All of these resources can be used to help you complete the short quiz associated with this week's lesson. As always, feel free to reach out via comments in our Google Classroom or via email. We're always here to help.